This is Nighttime Mathematics Radio. If anyone has any math questions, feel free to tweet them to @nightmathradio.com and I'll answer them right here on the air. Well, we had an interesting question that came by earlier today. I'll start with that one while we're waiting for people to tweet in. The question looked like this. Let's take a look. We have a nice circle like this. And then the graph itself looked like, one second while I get down to it. We had a secant going across from S to J. Here's the circle E over here, the center of the circle E over here. Another point on the circle B down here. And we were told two things. We were told that this angle is 40 degrees, and we were told that the radius of the circle was 16 centimeters. And we were asked to find the measure of arc JB. So this problem basically comes down to remembering one theorem from geometry. And this is the way a lot of math works, by the way. A lot of math, there's key theorems that you prove that are tricky to prove, but once you've proved them, you don't have to prove them anymore. You can just use them from then on. And this is a particularly famous one. See, an angle like this, created by two secant lines like this, is called an inscribed angle. Or more simply, just an angle where the pointy bit's right on the edge of the circle. And it turns out there's a relationship between the angle, the inscribed angle here, and the central angle for that same arc, for this arc JB here. It turns out, and it's a bit fiddly to prove, but I'm sure it's proved in your textbook. I won't prove it now because that would take the entire show. That the inscribed angle is always exactly half the central angle. So if the inscribed angle is 40 degrees, the central angle is 80 degrees. Now they ask for the measure of the arc, and there's two different ways to measure an arc like this. You can either take an angular measure, or you can take a linear measure. You can say how long is that arc length. The first one's easy. The way you find an angular measure for an arc is you just find literally the central angle that subtends that arc. Here we've got that. We know the central angle is 80 degrees, so that's the measure of that arc. Now that's fine as far as it goes, but often what you really care about is the arc length. So how do we find the arc length? Well, you know the length of the entire circumference, where the circumference is equal to pi times the diameter. How do you know that? Well, that's literally the definition of pi. Pi is the circumference divided by the diameter. That's how pi is defined. Well, we're not given the diameter, but we are given the radius. We're told the radius is 16 centimeters. And the diameter is just twice the radius, so that's 2 times pi times 16 centimeters. Or 32 pi centimeters. We're not being asked the entire circumference, we're being asked for this arc length. And now here's where having the angle measure helps you. When you have the angle measure, that fraction of the entire circumference is in fact the length of the arc. So in this case, what do we mean by that fraction? Well, the entire circumference is 360 degrees. That's all the way around the circle. But in this case, the length of the arc is just equal to 83/60ths of the full circumference of the circle. This simplifies nicely. 80 over 360 is 8 over 36, which is 4 over 18, or 2 over 9. So that's 2/9 times 32 pi centimeters, or 64/9 pi centimeters. Now you notice at this point I've been carrying it around as an exact answer, but at this point, usually at the end of a thing, since this is a word problem, the circle is 16 centimeters, this is a real thing in some sense, we should figure out an approximation for this. So now at this point I'll grab my calculator. Now before I plug things into my calculator, let's take a look at this for a second. How big is 64/9? Well, we sort of know this. 9 times 7 is 63, so that's very, very, very close to 7. Pi is a little bit bigger than 3, so this is a little bit bigger than 7 times a little bit bigger than 3. So we'd expect our answer to be in the neighborhood of 21, 22 centimeters. It's always really, really worth thinking things like that through. If you don't think things like that through, whatever your calculator tells you, you're likely to believe. And any mispush on your calculator will give you a massively wrong answer, which is embarrassing. Being a little bit wrong is not a problem. Being wildly wrong is. So this is, once again, 64 divided by 9, which we said was very, very close to 7. In fact, it's 7.11111, times pi. This calculator has a pi button right there, times pi. And there's your answer. In fact, I said it was a little bit bigger than 21, and in fact, it's 22.3. So it's about, now how accurate is this? Well, we were told it was 16 centimeters. That has 2 significant digits, so we should probably hold 2 significant digits here. That's about 22 centimeters. And there's our arc length. Now that, looking at this, you see that 80 over 360 and say, ugh, that's ugly. Why do I have to have that? The reason we have to have that is that we're using degrees. This is the fundamental reason why radians were defined. Because remember, the way radians were defined is, if this is our arc length L, I'll just call this L for the moment, the way radians are defined is that this angle up here, I'll call it theta for the minute, is just equal to the radius times, the radius divided by the arc length. Ugh, I've got to be completely backwards. Theta is equal to the arc length divided by the radius. So if we were using radians, all we would have to do is multiply by the radius and we'd be done immediately. But in this case, sadly, we don't have that. Now, this, by the way, is another place where there's that fight between pi and tau comes up. Because the question comes, which are you more likely to have, the radius or the diameter? Because if you'll have the diameter, again, you can see from that definition here, from the math that came in here, all of this would have been much more straightforward with tau instead of pi. So, sorry, if you have the radius. If you have the diameter, then just pi is more obvious. So the question is, do you think you're more likely to have a radius or a diameter? And that comes down to, are you more likely to be getting this thing from measurement, or are you more likely to be getting this thing from, say, pure math? If it's coming from pure math, then the radius is the more important thing, and we should be using tau. If we're getting this thing from measurement, the diameter is the more important thing, because that's something you can measure with calipers in a lab, and therefore pi is the more likely useful thing. This is Nighttime Mathematics Radio. Okay, that was that question. It was an interesting one from earlier. Now, let's go back to Twitter and see if anyone's asked us any questions. I have no questions yet, but once again, Nighttime Mathematics Radio is on the air, so feel free to ask a question anytime. This is Nighttime Mathematics Radio coming to you live with the best math help and the worst loops that Apple has available. Ask questions via Twitter at nightmathradio.com and we'll respond to them live on air. This is Nighttime Mathematics Radio, coming to you live from our secret base by the San Francisco Bay. If you have any questions, ask them to be live here on Twitter, and we'll respond live on the YouTube. This is Nighttime Mathematics Radio. For now, you can sit back and enjoy the weirdest, lamest loops that Apple has to offer. This is Nighttime Mathematics Radio. Well, while we're waiting here, let's take another look at the TI-30XA. This is the very cheap calculator that we often show off on this channel. It's $20, but For 20 bucks, it gets you a lot. It doesn't get you everything that 140 would give you with the TI-84, but 20 bucks is cheap. Actually, this one, and you can get this as cheaply as 12. So let's see what we can do with 12 bucks. And the answer is, actually, as I say, really quite a lot. Let's turn it back on again. Clear out the stuff we were just doing. Now, inverse trig functions are a little funny. They're hidden on this thing. You see sine to the minus 1. And the problem here is that the notation is really strange. So the notation for trig functions is maddening because it doesn't actually make that much sense. For example, if we want to square sine, if we want to take sine x squared, there's a short form of writing that everyone's familiar with, that you write sine squared x. If you want to cube it, similarly, you can write sine x cubed is equal to sine cubed x. So you would think by this logic that if you want to take 1 over sine x, that would just be sine to the minus 1x. That would make sense. That would follow the same pattern as here. Unfortunately, that's not the way the notation works. So this is wrong. That's really a shame. It makes things very complicated. Instead, when we say sine to the minus 1, what we mean is the inverse function of sine x. What we're in fact taking here is the functional inverse. And you remember, you did a unit on functional inverses back in algebra. We made a big deal that as long as a function passes the horizontal line test, you could find an inverse function that will undo the action of the function. So you say, wait. Because you think about what sine looks like. Sine looks like this. It starts at 0. Then we get out to, and I'll use radians for the minute, but you could easily use degrees. Get out to pi over 2. Increases, it becomes 1. Then by pi, it comes back down again. And is 0 again at pi. At 3 pi over 2. Drops all the way down to negative 1, where it goes flat again. And then at 2 pi, it comes back up to 0. And then does that over and over forever. So that oscillation goes on and on and on and on out forever. And now at this point, you're probably thinking to yourself, wait. In what possible sense is this an inverse? This can't be invertible. This doesn't pass any horizontal line test you could possibly imagine. In fact, any horizontal line you draw will cross the sine function an infinite number of times. So how could we possibly have an inverse sine function? I mean, you can see it. It's drawn on the calculator, so obviously there's some way to do it, but what on earth are we doing? And the answer is we get cute. And this is why we spent a very long time, way back in algebra, talking about domains and ranges of functions. What we say is, well, over the natural domain of sine x, that is over every number it makes sense to plug into sine x, and every number makes sense to plug into sine x, you could plug any real number in, then yes, sine is not an invertible function. But we can restrict sine. We can say, well, what if we said instead that our domain just runs from minus pi over 2, here, where it's at negative 1, up to pi over 2. So what if we, instead of having the domain be minus infinity to infinity, what if we just say, okay, new function, it's exactly like sine x, but it only exists between minus pi over 2 and pi over 2. And the answer is, well, okay, that really does pass the horizontal line test. Because now the function doesn't exist out here, where it starts wiggling up and down again. It doesn't exist back here, where it wiggles up and down forever. It only exists between minus pi over 2 and pi over 2. That function you can invert, and that's what's meant when you write sine to the minus 1 of x. What you're saying is, what's the point between minus pi over 2 and pi over 2, if you're in radians? Or what's the point between negative 90 degrees and 90 degrees, if you're in degrees? Or what's the point between minus 100% grade and 100% grade, if you're in gradients for some mysterious reason? That would give you this sign. So, for example, and let's see, my calculator currently is in degrees, so that's fine. I could say, sine of what is minus 1? So I put minus 1. So if I put 1 in, there's minus 1. If I say second inverse sine, it says negative 90 degrees. That's where it becomes minus 1. If I say, how about 0.5 minus? This is, by the way, a little bit weird. You can't type minus 0.5 on a $12 calculator like this. And the reason is this doesn't really write math the way a human thinks about math. This doesn't have a button to say, give me the negative sign. What this gives you, this has is a button here which shows a plus and a minus swapping. This says change the sign of the number that's there right now. So if I push this first, well, the number that's usually there when I start typing things is 0. So if I change its sign, it says, okay, change the sign, still 0, done. And if I type the 0.5, it goes, okay, positive 0.5, you're done. So for a cheap calculator like this, you have to first type the number and then hit the plus minus sign. But at any rate, now that I've done that, I can type second inverse sine. It says, yep, negative 30 degrees, and that's correct. That is, if you've memorized all those sort of common sines and common cosines, negative 30 degrees is the thing that if you take the sine of it, gives you minus 1/2. Why? Well, that's one of those special triangles you probably memorized way back when. That's a 30, 60, 90 right triangle. So that's how that works. So that's terrific. It does let you take an inverse of a sine function, and you can do something similar with cosine functions. Let me make a little more space for myself by turning the page. On our nice clean page here, let's look at a cosine function. Well, a cosine function starts up here at 1, because remember, a cosine function is, oops, drawing off the page. Remember, the way both these things are defined, once you're in grown-up trigonometry, and you're done with SOHCAHTOA and things like that, you think of a point going around the unit circle. Then cosine gives you the x value, so it starts here at 1, then comes back and ends up being 0 when you're at 90 degrees, then goes all the way back to minus 1 when you're at 180 degrees, then back to 0 when you're at 270 degrees, and back to 1 again when you're at 360 degrees. So what I just said was this. And this time I'll use degrees for no particular reason, except they're easier to recognize on the calculator. So at 90 degrees here, it goes through 0. At 180 degrees, it goes through minus 1. At 270 degrees, it goes through 0 again. And here at 360 degrees, it goes back up to 1. So that's all well and good, except you notice now the domain restriction we used last time, minus 90 degrees to 90 degrees, wouldn't work for cosine because it fails the horizontal line test between minus 90 and 90. Instead, we cut it between 0 and 180. Because there, inside this region, it passes the horizontal line test and is an invertible function. So cosine to the minus 1 always gives you a number between 0 and 180. That can get very, very confusing. If you are taking inverses of sines and cosines, you have to remember where each one is going to give you a point. Especially if you're in a problem where there's no reason why your answer should be in that range. Because you're going to have to back out and get all the answers. So it's going to be a little bit tricky to back everything out again if you've forgotten what the natural one is. And so exactly we see this on our calculator again. Let's take the same kinds of points, say minus 1. They'll take inverse cosine. And it gives you this time 180 degrees. Which makes sense because that's the cut it's using. If I say 0 inverse cosine, it gives me 90 degrees. If I take 2 inverse cosine, it tells me error, which is correct. Because what I just asked it is, what angle has a cosine of 2? And the answer is, don't be silly. No angle has a cosine of 2. Cosines always live between minus 1 and 1. So the calculator rejected it. It very spectacularly wrote error at us. How about tangent? Well, tangent's a little bit even funnier. Because remember, what tangent is the slope of the line going through the origin and through a point on the unit circle. So it starts at 0. As you go upwards, it goes upwards to 1 when you're at 45 degrees. And then it shoots upwards, because remember, a vertical line has an undefined slope, and the slope gets closer and gets larger and larger and larger as you get close to it. 1 million, 1 billion, 1 trillion. So on the same graph here, the graph of a tangent looks kind of funny. It starts at 0. When you get out to 45 degrees, it goes through 1. Then at 90 degrees, it actually hits an asymptote. It goes all the way up. Bam! Then the moment you get a little teeny... So then at 90 degrees, it doesn't even exist. Because now we're saying, what's the slope of a vertical line? And the answer is, don't be silly. There is no slope of a vertical line. That's not something you can ask. Then, as you get past 90 degrees, it's suddenly enormously negative. So it comes back in from the bottom of the asymptote. Then comes back up, and at 180 degrees goes back to 0 again. Because now we're looking at the slope of the line going from here backwards through 180 degrees. And you notice now we're back on the same line we started with. We're just looking in the opposite direction, but that's the same line with the same 0 slope, and so it'll repeat over and over again from here. So it turns out for inverse tangent, we just choose the point between minus 90 degrees and 90 degrees that makes sense. So if we say 1 inverse tangent, we get 45 degrees. If we say minus 1 inverse tangent, we get minus 45 degrees. If we say a big number inverse tangent, we get something that's very, 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 very close to 90 degrees, but not quite there. If we say, let me clear this out. If we say negative very, very, very large magnitude number, so a very, very negative number inverse tangent, we get negative number that's very close to minus 90 degrees, but isn't quite there, because you could never quite reach it. I mean, you can reach it as far as the calculator can see, but that's about as far as you can get. So those are the inverse trig functions: inverse sine, inverse cosine, inverse tangent. They're really useful as long as you remember what you're actually doing. And it's really easy to forget what you're actually doing, so it's worth paying attention to. By the way, one more note for this calculator. This is just something else. A few episodes back, we were looking at how to do simple statistics on this calculator. I noticed it still says stat up there, which means there's still stuff in the statistical registers. Pushing clear doesn't get rid of it. And we can see that. If we ask how many points do you know about, second number, it says 5. I still know about those 5 points you told me about a couple of weeks ago. Thanks, calculator. So how do we clear them? Well, you see above the 7, there's a CSR. That means clear statistical registers, which is calculatorese for forget all that stats. So second CSR, the stat thing goes away. If I now ask it how many points do you know about, it says error. I don't know at any points. What are you talking about? You haven't told me anything yet. Which is what we wanted to see. So this is Nighttime Mathematics Radio. Again, if you have any questions, I'll stick around for another 5 or 10 minutes here, and then I'm going to go off air. So, this is Nighttime Mathematics Radio. This is Nighttime Mathematics Radio. Now, an interesting question just got posted to Twitter. It wasn't posted to me, but I'm going to answer it anyway. So, let's take a look at this one. The question looks like this. We're told that, let me pull this one back up again. We're told that sine t is equal to x over x plus 1. And asked to find the inverse tangent of x over the square root of 2x plus 1. So how on earth are we going to do this? Well, let's figure out the other trig functions using some really simple trig identities. Oops, let's pull this down. We know sine t, so we also know sine squared t. That's x squared over x squared plus 2x plus 1. Why would I think to do that? Well, I see that 2x plus 1 there. That looks really suspiciously like the denominator squared. So let's start playing around with Pythagoras' theorem to see where we can get. Well, what's cosine squared t? Well, we know that sine squared t plus cosine squared t is 1, so cosine squared t must be equal to 1 minus x squared over x squared plus 2x plus 1. So, by usual fraction math, that's equal to x squared plus 2x plus 1 over, minus x squared over x squared plus 2x plus 1. Difference out the x squared, so we get 2x plus 1 over x squared plus 2x plus 1. So there's cosine squared t. So now we have sine squared t and cosine squared t. That's kind of cool. How about tangent squared t? Well, we can divide one by the other. That's sine squared t divided by cosine squared t. The denominators are the same, so they cancel out, so we get x squared over 2x plus 1. Notice that both denominators are exactly the same, so they both cancel. So all that we had left is the fraction of the numerators. It's x squared over the quantity x plus 1 squared divided by 2x plus 1 over x squared plus 2x plus 1. Now there's one tricky bit here, which is we're not actually told very much about the signs of these things. That's okay. We're not told about the sign of x, but we can more or less work it out. We can say, so what's tangent t then? Well, if x were positive, then we could just take a square root of the top and say, well, that's then just x over square root of 2x plus 1. If x were negative, that would still work, because remember, sine x was originally x would be negative in that case, so that's we have the correct sign anyway. And so now we're being told, well, what's the tangent of what is equal to this thing? And we just figured it out. It's t. And that was your answer. This is Nighttime Mathematics Radio. Okay, it's coming up on 10:40, which is probably a good stopping point for the program. As always, come back every Saturday night at 10 o'clock Pacific, 11 o'clock Mountain, midnight Central, or 1 in the morning on the East Coast, and we'll try to answer your math questions for you. This is Nighttime Mathematics Radio, signing off.